The kinetics of this reaction is given by this equation. I'm not going to go into it. This is a standard equation for reaction kinetics called an activated energy reaction. The activated energy is this E star right here. Okay? These are the constants involved. This is the energy for the process of the formic acid and the glycine forming this intermediate called a complex, and then forms the products. The energy of that product complex is calculated to be minus 17 kilocalories per mole. If you calculate K, it's 1.9 times 10 to the 25th reciprocal seconds. It's a fast reaction, of course. But remember, 10 to the 25th power, okay, which is quite favorable. Now, let's look at the alternative. What if all the glycine was not reacted? Let's suppose you had some left, just by chance. Then two glycine molecules could come together and they could interact and form a peptide bond, okay? When they do, you would get that resulting product and the same other thing, the hydronium ion, okay? But this is the positive energy. A smaller energy, 5 kilocalories. It's less energy satisfying than the previous reaction, right? I mean, it's, at least, 3 times smaller, energetically speaking, okay? So the constant that you calculate for that is 10 to the 16th power, not 10 to the 25th power. It's less favorable kinetically, right? Okay? So the energy of that peptide bond is 21 kilocalories smaller than the energy of the glycine forming the bond with the formic acid. And that's a critical difference right there. A lot of difference, okay? The thermochemistry of that says if you take the energies of the bonds on this side of the reaction, 423 kilocalories total, subtract the energies of these, 412 kilocalories, you get a positive energy change by 11 kilocalories. What happens? Can it occur automatically, spontaneously? No. Positive energy change does not occur spontaneously, does it? I just showed you that. This is the proof. You could never get it, even if the glycine molecules were there. Doesn't make any difference. If you change it to adenine or any other amino acids, you're going to have the same problem, no matter what. You could never get the favorable reaction to go automatically without some involvement of a catalyst or such. Okay? What's the bottom line? This is the bottom line, obviously. Chemical reactions impossible for amino acids present in Miller's mix because the products can even form one peptide bond, much less polypeptides, which are needed to form proteins. It cannot happen. It can't happen based upon the results that are produced from those experiments. Now, in spite of that, we have a few things I wanted to just share with you on the side here. Well, first of all, let me share this other thing with you. And this is the end of the talk, obviously. This, by the way, if you hadn't gotten a hold of this book by design, Jonathan Sarfati, you want to get it. It's an excellent book. Got a lot of good stuff in it with a lot of good references. Does a real good job. Jonathan is a physical chemist. It says here, with regard to amino acid folding, protein folding. Remember how important I told you that was, protein folding? It said, despite the enormous, what they did is the IBM, back in 2005, constructed a supercomputer called the Blue Gene. And that computer was, the first problem it was going to attack was protein folding mechanism, okay? And it wasn't going to be the most complex protein folding, it was going to be the most well understood or the most accessible protein folding. It says, however, despite the enormous computing power, they estimated it would still take about a year for the Blue Gene to finish the calculations of the folding of a simple protein, which it only takes a second in the natural process. Only takes a second. But it's going to take a year for that supercomputer to do it. Okay? To do the same process, in other words. Okay? And of course, they say, one IBM researcher said, It's absolutely amazing, the complexity of the problem and the simplicity with which the body does it every day. Oh yeah, it is truly amazing, isn't it? But it's evolution, right? It's natural process, right? Yeah, we know better, don't we? Yeah, sure. Here's another cutie thing I just got off the internet about a day or so ago. Without an enzyme, biological reactions essential to life would take 2.3 billion years. Well, I'm not surprised. Without an enzyme. This was a report that came out of, see, was a source. I think the source was, Science Daily, November the 11th. And these Professor Richard Wolfensden, who's a distinguished professor of biochemistry and biophysics at North Carolina, Chapel Hill. And he is reporting that without a particular enzyme, a biological transformation necessary to assemble, essential to assemble and create the building blocks of DNA and RNA would take some 2.3 billion years. Enzymes can make that reaction happen in milliseconds. Reduces 2.3 billion years to milliseconds with enzymes, okay? Then he goes on to say a lot of stuff here. It's a lot of gobbledygook. And he says more gobbledygook. We've been defining here is what evolution had to overcome, that the enzyme is surmounting a tremendous obstacle, a reaction half-life of 2.3 billion years. Now look, evolution has to overcome that. So it can do what? Create this enzyme to do the job the way it does it. Evolution does that. Would you believe it? That's what he says here. Knowing how long reactions take place without enzymes allows a biologist to appreciate their evolution as prolific catalysts. Their evolution, not creation, their evolution as prolific catalysts. The mindset. Here's another one. Evolution's new wrinkle. This came off of the